Physicists say that the universe had its origin in an event known as the Big Bang approximately 13.7 billion years ago. However, the question that arises is what caused that explosion and why did it occur? Over time, we have been researching and studying the science and history of our universe, and the Big Bang has been the predominant explanation for everything we have observed. There have been countless studies, and thousands of scientists have worked on their research, with the data collected always supporting the Big Bang theory as the main explanation for how the universe was formed. According to this theory, dark energy is a form of energy even more abundant than galactic energy, and is considered the anti-gravitational force responsible for the continued expansion of the universe since the Big Bang. Science today is very different from what it was in the past, and with technological advances, new theories emerge. Many times, we discover that things we thought to be absolutely true are far from being so. Michio Kaku has raised the official debunking of the Big Bang. This is because the James Webb Telescope has detected 750 new galaxies that look nothing like what was expected. This raises a new perspective and leads us to delve deeper into how the James Webb Telescope is changing our understanding of the universe as a whole. Join us on this incredible journey beyond the far reaches of the observable universe to discover more details about the immense number of new galaxies that have been discovered. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video, share it to reach more people, and turn on the notification bell. The images of new galaxies captured by the James Webb Telescope are absolutely stunning. In a single image, we can see hundreds of galaxies all together, and the beauty and power of these photos are striking. However, what seems to amaze the average person is precisely the opposite for researchers. These images are amazing to them, but they do not match what the scientists expected to see based on their theories. In fact, many more galaxies are being seen than expected, and these galaxies are different from the rest. They are smaller than imagined and have a truly remarkable age. These surprises are generating some panic among scientists. There is even an article that begins with the word panic in its title, which shows the seriousness of the situation. These galaxies are nothing like what they were supposed to be according to established theories. For a long time, scientists have proposed the Big Bang theory as the main explanation for the origins of our vast universe. According to this theory, approximately 13.7 billion years ago, the universe began its existence through some kind of mysterious cosmic event. However, these new images challenge the definitive story of the birth of the cosmos as previously understood. These striking images captured by the James Webb Telescope have challenged our understanding of the origins of the universe. Specifically, these images directly contradict the Big Bang hypothesis, which has long been considered an unquestioned truth by most cosmology theorists. The galaxies captured in these images appear to be too small, smooth, old, and numerous compared to the predictions of the Big Bang hypothesis. The fact that the observed galaxies are 2 to 3 times smaller than similar galaxies imaged by the Hubble Space Telescope completely defies the expected behavior in an expanding universe. According to the hypothesis, as the universe expands, objects should appear larger as distance increases. However, these James Webb observations show galaxies that defy that expectation. Moreover, the smoothness of these galaxies is totally unexpected. According to the Big Bang theory, galaxies should show irregularities and variations in their structures due to the dynamics of their formation and evolution. However, the images reveal unusually smooth galaxies without the level of complexity and roughness that one would normally expect to see in galaxies of their age. This defies the expected time sequence for the formation and evolution of galaxies within the framework of the Big Bang theory. At the beginning of the universe, all matter, energy, and building blocks of the cosmos were compressed into an extremely concentrated point called a singularity. At this point, the density reached an infinitely high value due to the extreme compression of matter and energy. The concept of singularity is based on our current understanding of the laws of physics, especially the equations of general relativity proposed by Albert Einstein. Within the singularity, all matter and energy in the universe existed in an extraordinarily compressed form. This extreme density implies that an enormous amount of mass and energy was concentrated in an infinitesimal space under extreme pressure and density conditions. The temperature within the singularity would exceed any temperature observable or reducible in our current understanding of the universe. The energy stored in this hot, dense point was the seed from which the entire universe as we know it originated. The singularity marked the beginning of the universe, the origin of everything in our cosmos. After the initial singularity, the universe began its journey of expansion and inflation. This process occurred over approximately 13.7 billion years, giving rise to the universe as we know it today. The expansion of the universe began with an extraordinary and rapid burst known as cosmic inflation. During this phase, the universe expanded at an unimaginable speed, far exceeding the speed of light. It is as if the very fabric of space stretched and stretched, pulling everything within it with it. Cosmic inflation played a massive role in the formation of the large-scale structure of the universe. It smoothed out irregularities, homogenized the distribution of matter and energy, and paved the way for the subsequent formation of galaxies, stars, and other cosmic structures. As the universe continued to expand, the rate of expansion gradually slowed. It is important to note that although there was rapid cosmic inflation in the initial period, the universe continued to expand at a measurable rate. This steady expansion is known as cosmic expansion or the expansion of the universe. Scientists have observed the effects of this expansion through various observations, such as the redshift of light from distant galaxies. Redshift indicates that as the universe expands, light waves are stretched and shifted to longer wavelengths, moving them toward the red end of the spectrum. During the expansion, all the stuff that makes up our universe was compressed into an incredibly small volume. It was clear that matter cannot survive in such a compact space, so transformations occurred as the universe expanded and cooled. Particles such as protons, neutrons, and electrons began to interact with the light and energy around them. These interactions played a key role in the formation of matter in the universe during the first few minutes after the Big Bang. This process is known as nucleosynthesis. Chaotic and disrupted galaxies due to multiple collisions were expected to be observed, but the images captured by the James Webb Space Telescope tell a different story. Instead of chaotic galaxies, the images reveal well-organized disks and spiral structures similar to the galaxies we see in today's universe. This unexpected observation challenges the idea that mergers are a common process in galaxy evolution. If these new galaxies have not experienced many or any mergers, it becomes unlikely that small galaxies will grow and become hundreds of times larger as expected. This implies that these galaxies were never small originally. Furthermore, the optical illusion predicted by the expanding universe hypothesis, where objects appear smaller due to expansion, does not hold in this case either. Therefore, what we have believed so far turns out to be a falsehood. In addition, the age and abundance of galaxies revealed by the James Webb Space Telescope also challenged the validity of the Big Bang theory. The JWST is equipped with filters that allow imaging in the infrared part of the spectrum, which facilitates the study of the colors of distant galaxies. By analyzing these colors, astronomers can estimate the age of stars and galaxies. Recent findings from the James Webb Space Telescope, JWST, have caused significant shifts in our understanding of cosmic evolution. The unprecedented resolution and sensitivity of JWST have allowed astronomers to peer deeper into the universe than ever before, revealing details that challenge our established theories. For instance, the telescope's observations have unearthed galaxies that appear far more mature and organized than expected for their purported ages. This contradicts the traditional view of a chaotic, more disordered early universe. Researchers are particularly intrigued by the discovery of galaxies that exhibit well-defined spiral structures and smooth disks, which seem to have formed earlier than theoretical models predicted. This observation suggests that the processes governing galaxy formation might be more complex and varied than previously assumed. One possible implication is that the formation and growth of galaxies could have occurred differently, potentially involving mechanisms not fully accounted for by existing theories. Additionally, the JWST has identified a surprisingly high number of galaxies in the early universe, a finding that could necessitate a re-evaluation of how galaxies cluster and interact. The presence of these numerous and relatively small galaxies raises questions about the role of mergers and collisions in galactic development. If these smaller galaxies did not experience as many mergers as expected, this could imply a need to reassess the models that describe galactic growth and evolution. Moreover, the advanced infrared capabilities of JWST have provided new insights into the star formation rates within these galaxies. The ability to detect faint, distant galaxies and observe their stellar populations allows scientists to gauge how quickly stars formed in the early universe. This data may reveal whether the early universe was as densely populated with stars as current models suggest, or if there were significant delays in star formation. The implications of these findings extend beyond just galaxy formation. They could impact our understanding of cosmic structures on a broader scale, including the distribution of dark matter and the nature of dark energy. If the observed galaxies defy the predictions of the Big Bang Theory, it could lead to new theoretical frameworks that better account for the complexities of the early universe. In conclusion, the new data from JWST is not just refining existing theories, but is also pushing the boundaries of our knowledge, potentially reshaping fundamental aspects of cosmology. As astronomers continue to analyze these revelations, they will undoubtedly engage in a rigorous process of theory adjustment and refinement. The unexpected discoveries serve as a reminder of the dynamic nature of scientific inquiry, where new evidence continually refines our understanding of the cosmos. The recent revelations from the James Webb Space Telescope, JWST, have sparked a significant reevaluation of several core assumptions in cosmology. Beyond the immediate implications for galaxy formation, these discoveries prompt a broader re-examination of the universe's structure and evolution. One major area of interest is the role of primordial black holes, which are theoretical entities that might have formed in the very early universe. If these black holes are present in the quantities suggested by some new observations, they could have influenced the formation of galaxies and the distribution of dark matter in ways that have yet to be fully understood. Additionally, the JWST's findings raise questions about the consistency of dark energy and dark matter models. Dark energy, which is thought to drive the accelerated expansion of the universe, and dark matter, which affects galactic formation and motion, might need to be redefined or supplemented with new theories to account for the observed discrepancies. The unexpected characteristics of the newly discovered galaxies could indicate that our current understanding of these dark components is incomplete. Furthermore, the telescope's high-resolution imaging has enabled astronomers to study the chemical compositions of these ancient galaxies in unprecedented detail. This analysis could provide insights into the early stages of chemical enrichment in the universe, shedding light on the processes that led to the formation of heavy elements and their distribution throughout the cosmos. Such information is crucial for understanding how galaxies evolve and how the building blocks of life were distributed in the early universe. The JWST's data also offers a unique opportunity to test theories about cosmic reionization, a period when the universe transitioned from being opaque to transparent as the first stars and galaxies formed. By examining the light from these early galaxies, scientists can gain a clearer picture of how reionization occurred and the factors that influenced this pivotal phase in cosmic history. Moreover, these findings highlight the importance of continued observational and theoretical work to refine our models of the universe. As new data is collected and analyzed, scientists will need to integrate these insights into existing frameworks or develop new models to accommodate the emerging evidence. This ongoing process underscores the dynamic nature of scientific discovery and the ever-evolving quest to understand the universe's origins and its fundamental workings. In summary, the JWST's groundbreaking observations are challenging long-held assumptions and opening up new avenues for research. The implications of these discoveries extend well beyond galaxy formation, potentially reshaping our understanding of fundamental cosmic processes and the universe's underlying structure.